Alright, so for part A, we're trying to find the impedance, and if you look at the impedance formula, which is right here, we don't have a capacitor in our circuit, so we can ignore this part, and so just plugging in what we have that the impedance is Z equals the square root of R squared plus omega L squared, because you use what XL equals here.
Alright, so for part B, we're trying to find the amplitude of the current. And so from our given function, we know that the amplitude V max is equal to V naught. So here we have that V naught equals I max times the impedance. So to find the amplitude of the current, we would just plug in our impedance in for Z. So we get V naught equals I max times the impedance, which is square root of R squared plus omega L squared. And then we solve for I max, so we divide by both sides and we get that I max equals V naught divided by the square root of R squared plus omega L squared.
Okay, so we're going to plug into delta V sub R, we're going to plug in the I max, so it's just going to come down to the amplitude of the voltage across the resistor is equal to V naught over square root of R squared plus omega L squared R sine omega T.
So for the voltage across the inductor, we're just going to take the I max just like before with the voltage across the resistor and plug it straight into the equation here that we were provided in class. So the amplitude of the inductor is E naught divided by impedance times omega
Okay, so to find when the angular frequencies are equal, we can just take the amplitudes from these two equations and set them equal to each other. So when you write that out, set that equal to this amplitude over here. Alright, and then if we're going to solve for omega, you can see that these are going to cancel out as well as the voltages on top. So you're going to be left with R equals omega times L, so the angular frequency is going to be the resistance over the inductance.
Okay, for part F, we're looking for what happens when omega is a very large number, what happens to the amplitude of the inductance. So, in order to do this, we're going to just take a limit as omega tends to infinity. Infinity is a very large number, so when we put it in here, essentially this is going to cancel with this because the R squared is going to become irrelevant when you have an infinity in the bottom. Infinity squared, square rooted, will just be infinity. So this will get canceled with that, and we're just left with V naught.
Okay, so now we're going to see what happens when omega gets really, really small. So basically you can just picture that omega is going down to 0 because 0 is the smallest it can get since it can't be negative. So in actuality, all of this goes to 0.